everyone, today we are moving away from talking about polynomial functions to talking about rational functions. Rational functions are going to begin on page 161 because we're skipping lesson 12.1 and we're just jumping right into 12.2. So we have a rational function here given talking about the representation of Sarah's age to Corey's age, where x represents the number of years from now, either past or future. So if we look here on this particular graph, we have a domain given of -6 to 18, and then our range is kind of moving from 0 to 44. And if we graph this, if we use our graphing calculators to look at this, we have the ages typed in. And again, if you have an older calculator and you don't have a fraction, make sure you're using parentheses around the top versus the bottom to make sure order of operations is working correctly. And if we adjust the window so that it matches the graph given to us with the correct domain, scale on the graph being 1.5, and then 0 to 44 with a scale of 4, we'll see our graph here of this rational function. So what we're noticing here on the graph itself then is what's going on here with the values of x as we get closer to -6. Well, what's happening is as x gets closer to -6, the denominator gets closer to 0. Right? And what we're seeing here is when you divide by a smaller answer, you're going to get a larger number. So as these numbers are getting bigger or smaller, then the answers will get much larger, and that's what we're seeing here as we get closer to the asymptote, right? And then from there, as we move down here, what we see is the shape of the graph, it becomes vertical near x equals -6, saying that it's increasing without bound. So it's going towards that positive infinity value. If we were to observe this graph from a distance, zoom out on our calculator, it would appear that it merges with that vertical line. So notice the term here, bounded, if it's constant, kind of approaching a value, as to where here it's approaching infinity, so it's not bounded. What we have there is that vertical asymptote, which is kind of that vertical line that it appears that it's approaching. So in this case, our vertical asymptote would be x equals -6 would be our vertical asymptote. And yeah, that's our straight line there. And looking at this graph, why is it actually never going to officially be vertical, even though it might look that way in our graphs? Well, the answer is it still needs to be a function, right? So it still has to be a function. So even though it looks like it's going to approach that vertical line, it's never actually going to be vertical because it has to pass that vertical. So be aware, even though it looks vertical and we approach that asymptote, it's really always going to have, just because there's an infinite amount of decimal values we can put there, that it's never going to really approach officially that value to not pass the vertical line test, because these are still functions. Okay? So what we see then, moving on to the next page, is that we also want to analyze what's going on with our calculator. So if we go back to looking at kind of the horizontal of this, what value is this approaching? So what you're going to do is you're going to hit second window, you're going to look at your table, and you're going to make sure that you select the ask mode. Because what we're going to do for number 5 is we are going to look at what we think this is approaching for 5 and 6. So if we go then to the table, so hit second table, and we start typing in really large x values. So choosing what we want to type in. What we're noticing is that the larger the values we are typing in, the closer it appears that it is approaching 1. So as x is approaching infinity, it appears that the function r of x is approaching 1, okay, aka a horizontal asymptote at y equals 1, since it is a horizontal line, it will be y equals there. And again, it's kind of joining together about what the end behavior happens with the horizontal asymptote. There is a relationship between those two values on here. Now, if we look at the ratio of these ages, it would, it looks again to be converging towards 1, but the thing here is it's never going to actually be 1 because they're never the same age. But there's never, unless they were born the same day, which they weren't, in this particular problem, they are never going to be the same age. That's why it's never going to equal 1. And we can confirm this because if we try to set that function equal to 0, or excuse me, equal to 1, what you would notice is if we tried to get it to equal 1, we would end up multiplying both sides by the x plus 6, but then we would end up getting these x's to cancel, and 27 isn't going to equal 6. So we know that, and if we subtracted this over 21 isn't going to equal 0. Like, there's no way that these are going to work out, so that's why there's no solution, and they're never going to actually equal 1. It's just going to approach that horizontal asymptote. So again, what this is all leading us up to is the idea of rational functions. And what a rational function is, it's a function that is expressed as the ratio of two polynomials. So hence why we are transitioning from polynomials to rational functions, because there is that relationship with them. And again, we have these important features of these rationals, which are our asymptotes, both vertical and horizontal. Now, the parent function here of the rationals is 1 over x. And if we look at 1 over x and we look at the values of it, basically the biggest value with 1 over x is this 0.11 as well as -1 and 1. So we have this kind of picture here is kind of the parent function of our rational, which of course we could graph as well. To look here, if we clear out the original function here, 1 divided by x, and we just assume 6 to go back to a normal size table, we can see this. Now, we also can look at some values of our table. Reminder, we want to probably send this back to just non-ask mode, just back to auto mode, so that we can look at the table and see some values here. And what's going on here, we see at 0, we have that vertical asymptote happening. We see those critical points of -1, -1, 1, 1 to look at this parent function to be able to fill in this corresponding table here as well. So a couple of features about this graph. It has again, this is the parent function, right? And a couple of features here. It's got the vertical asymptote at x equals 0. It has a horizontal asymptote at y equals 0. So both of those are happening with our graph here. The domain on this one is going to be affected by that vertical asymptote. So we have here that x, such that x cannot equal 0, because we have that vertical asymptote happening here that is going to prohibit that. And for our range, what we're noticing here is that we are not passing through the x-axis, so our range then is all the y values except y cannot equal 0 as well. Our end behavior then is showing that we are, as we approach positive infinity, we're actually approaching 0. So as x approaches positive infinity, our graph is approaching 0. And that's actually going to go for negative infinity as well, because we see over here we're also approaching negative infinity. So we can actually write this as one feature, if we'd like, where we could say that as x approaches positive or negative infinity, we're approaching 0 on this particular one. We have different rates of increasing versus decreasing, because officially we are decreasing from left to right here, but then we're also decreasing from left to right here. But there is that break in our graph that we have to consider. So really we're decreasing the whole time throughout this thing. So if we look here, we're not increasing, but we're decreasing with a break. So from negative infinity until we get to 0, and then from 0 to infinity. Again, we have to consider that break in the graph though, so that's why that union occurs and we don't include 0. We have symmetry to the origin on this one. So we can flip our graph upside down and it looks the exact same. And that's pretty much our biggies here about this graph. If there's anything else to notice, feel free to jot it down as well. All right, now as we finish this out, we want to use a graphing calculator to help us with the final questions here, looking at these features. So if we go back to our graph here, they're asking us to look at 3x minus 2 divided by x plus 7. And if we look at this graph, what we are noticing here is that we have a shift compared to the parent function of what's going on here. And it's actually increasing without bound. And it seems like -7 is kind of our cutoff here. And actually, if we adjust our window a little bit, we'll actually see that there's another piece of this graph that we're just kind of missing in the normal Zoom 6 window. So if we extend that out to a little bit to the left. So question 12 asks us, is this increasing or is this decreasing without bound? It's kind of, if we look at the function itself, if we're increasing here as we approach -7 from the left, and then if we were to try and approach -7 over here, we would notice that it's decreasing as it gets to -7. Officially, the graph itself, though, is increasing throughout if we're moving left to right. But that -7, depending on which way you're approaching the vertical asymptote, it's increasing from the left, but decreasing from the right, which is an interesting thing to note. The vertical asymptote, then, we're observing here is occurring at -7. And for confirmation, in case we aren't sure, we can always look through the table and see that we have that error message occurring there. So we have that vertical asymptote for number 13 at -7. Our horizontal asymptote, then, is approaching the value of 3. And we see that as we start increasing without bound. Where is our graph going? It's approaching the value of 3. We're increasing, we're increasing, we're increasing until we get to about 3. So keep going on with this. So that horizontal asymptote at 3. Now we can also look at the equation itself to be able to determine what the vertical asymptote is, because we know the denominator of this is not going to be able to equal 0, otherwise it wouldn't exist. So that's where that vertical asymptote is occurring. So you can always use the denominator of your function in order to look at what that vertical asymptote would be. And we'll talk more about the shortcuts then to finding the horizontal asymptotes besides just spending time, scrolling through your calculator, y equals 3, to find the horizontal one in the upcoming lessons. Okay. Thanks everyone for watching. Practice more in class.